right, exponential growth and decay and logistic growth are the extensions that we're going to be doing for this unit. If you have not yet, if you don't feel comfortable solving for an exponent, this part of the unit is not for you. Go and find some practice in your packet to do with solving for an exponent. If you feel great solving all the equations that we've done, if you're an expert on inverses, then you've come to the right place to do a little more with this unit. So uninhibited growth or decay, you've seen models like this in Algebra 2 as well as in Algebra 1 actually. Uninhibited growth and decay looks like this. So the E there is not a variable. A sub 0 is your initial amount. The R here is your rate. And it's in decimal form. T is time, and usually the problem will tell you the time that you're using. And N of T is the number based on the time there. So this is your amount at some time. So a couple years ago, we had these modeling problems moved down to Algebra 2, but we lost some of the more difficult ones. And so I wanted to do a couple as an extension here so that you can get some experience with them. They're very good algebra. So example number 1 gives us a colony of bacteria, and we have uninhibited growth here. And our equation is N of T equals 90 e to the 0.05 T. So we're one the initial amount of bacteria. Well, the initial amount, you can get one of two ways. It's 90, because it's in the initial amount spot. And here we're measured in grams. The other way you can get that is to put 0 in for T. So anything to the 0 power is 1, so that just equals 90. What is the growth rate of bacteria? We have up there in the exponent, we have 0.05. Next to our T. What is the population after 5 days? So we're going to put T5 in for T. This is where function notation is really powerful. We have the input, we're going to get the output. You would definitely want a calculator for this. I get that this is a no calculator unit. I will make sure that anything that we do on the unit test, if you're doing an extension, you will get a calculator for, or I will just ask for the exact value. So you don't have to worry about that. If you put this into your calculator, put it in all as one step, exactly like that. You need to make sure that that 5 is up in the exponent, and you'll get 115.562 grams. So after 5 days, we went from 90 grams of bacteria to 115.562. How long will it take for the population to reach 140 grams? And how long will it take for the population to double? So these two questions have the same math going on with them. We're going to have to solve for the exponent. So what we're given is the amount at some time. We're given the N of T. And we want to find the time. So 140 is equal to 90 e to the 0.05 T. So in order to solve, remember, we want to get our exponential all by itself. We don't want to use ln yet. We need to isolate that e to the 0.05 T. So I'm going to divide both sides by 90 first. You can absolutely leave this as 14/9. You could use log or you could use ln. Clearly, since we have an e in this problem, ln is going to be the more efficient logarithm to use. Taking the ln of both sides allows us to pull down that exponent. Make sure you take the ln of both sides. Don't violate the equal sign. Two things left to do. One is recognize ln of e is 1. So here we have 0.05 times t times 1. So ln of e is gone. The other thing you want to do is get t all by itself. We are solving for t, so we're going to divide both sides by 0.05. You want to be careful here that 0.05 is divided by everything. We're doing ln of 14/9 and dividing it, the whole thing, by 0.05. That you can absolutely do in 2 steps in your calculator if you would like. Do ln of 14/9, enter, divide by 0.05. When you do that, you should get 8.837 days. The math for this next problem is very similar. Here we went doubling time for the population. So if we started with 90, our double would be 180. So we had to figure out what double is, but now the math from here is a little easier. We're not going to have that fraction to deal with. Same steps, divide by 90. 180 divided by 90 is 2, and so it's a little prettier than having that 14/9 to deal with. Going to take the ln of both sides. Again, ln of e is 1. And we're going to divide both sides by 0.05. Just be careful when you put it in your calculator. Make sure you close the parenthesis if you're doing it in one step. Close the parenthesis around that 2 before you do divided by 0.05. Here, we should expect more than 8 days. When I put ln of 2 and divide the whole thing by 0.05, I got 13.863. All right, logistic growth is on the other side. The logistic growth model is not a model that you need to know how to input into like you do the exponential growth, but it is one you should know how to work with. There's a little more algebra going on with this one. I like the algebra with this. I also like this because logistic growth models take into consideration carrying capacity, which means that they kind of have, you're going to have an upper end. And you may have seen this in your biology class, where you have a graph like this, and your carrying capacity is that top number. So we use this a lot. This is an application that's used a lot with animal populations because one certain area of, a park that's being studied can only can only have so many wolves in it. So you will see this kind of equation used for a lot of animal populations. So we're going to determine the initial population first. That means we're going to put in 0 for our t. And that is something that we need to put in. It's not like with the last equation where it was just that number in front. 230 is not our initial number of fruit flies. So we need to put in p of 0. We need to do p of 0 and do some calculator work here. If you don't know how to do a fancy fraction on your calculator, please, please, please ask me for help with that. It's a really easy shortcut. And once you practice it a couple of times, it will help you forever. You want to be able to put this in your calculator and make it look just like your handwriting. So you want to be able to do that stacked fancy fraction. This is much more painful if you try to do it with your, with parentheses. So when you put this in your calculator, you should get 4. We started with 4 flies. What's the population after 5 days? Once you have that in your calculator once, you can just go back and edit, and you can do it faster than I can write it. Again, the 0 up there and the 5 down here still mean they need to be in the exponent. I would definitely use parentheses there. And here, once you put that in, you should get 23 flies. Last question, how long does it take the population to reach 180 flies? All right, it's kind of gross, going from 4 to 180, but we're gonna do it. So 180 is our population, that's our P at some time. We need to find T. And in this problem, T is buried. It is in the denominator. It is buried, buried, buried. So we have to algebra our way out of this. So the first step is to get that denominator to the other side of the equation so that it's not in the denominator anymore. We're going to get rid of the fraction. Cancel the fraction first. Cancel that fraction first. And multiplying both sides by that whole denominator, even though it seems totally ridiculous, is the way to do it. I would not multiply that 180 through. I would leave that as 180 times that mess we just brought over. Because we're going to solve for T. So I'm going to divide both sides by 180 now. And that will let me get into that 1 and the 56.5 and the 8. So the next thing I'm going to do, I'm just going to divide away that 180. All right, 230 over 180 reduces to 23 over 18. Still solving for T. I'm going to subtract this 1 over. Since I'm not using my calculator yet, when I subtract 1 to the other side, 1 is the same as 18 over 18. That'll give me that common denominator that's nice. And let me keep that in fraction form. So I'm going to end up with 5/18 over here. And now we're going to need a calculator, because now we're going to divide by 56.5. Don't be shocked when you end up with a terribly small decimal here. You're going to end up with a terribly small decimal. 5/18 divided by 56.5, I got 0.0049. But now we're incredibly close to getting our T unpacked. So in order to bring that negative 0.37 T down, we need to take the ln of both sides. 1. And then I'm going to divide by negative 0.37. None of the steps in these problems are terribly difficult. It's all algebra. It's just having the confidence of going from one step to the other and like fine-tuning those algebraic steps. When I put that mess over there, ln of 0.0049, all divided by a negative 0.37, I got 14.374 days. Again, logistic growth models are really important. You have probably seen the idea of carrying capacity and logistic growth in your biology classes in the past. And hopefully, this kind of application is enjoyable to you. There's practice that follows this. You will see one of these as an option for you to do on the test to get up to 100%.